Hi, I'm Miss Hall, and this is Lesson 69, Evaluating the 6 Trigonometric Functions. The 6 trigonometric functions. Consider a right triangle that has an acute angle theta. The 3 sides of the triangle are the hypotenuse, the side opposite theta, and the side adjacent to theta. You can see it in this diagram. We have this acute angle is identified as theta. So we have the hypotenuse, I'll be indicating as H in our diagrams. Hypotenuse is always across from the right angle. We have the opposite side, which is the side across from theta, the opposite, and adjacent is another way of saying next to. Ratios of a right triangle side lengths are used to define the 6 trigonometric functions: sine, cosine, tangent, cosecant, secant, and cotangent. These 6 functions are abbreviated as such, and I'll be using the abbreviations in all my problems. So the core concept here is the right triangle definitions of these 6 trigonometric functions, and you are expected to memorize it, and I'm pretty sure you've seen all of this before. So the sine of theta is opposite over hypotenuse. The cosine of theta is adjacent over hypotenuse. The tangent of theta is opposite over adjacent. Now, those should be the 3 you're most familiar with. These next 3 are just reciprocals of sine, cosine, and tangent. So we have cosecant, and that's hypotenuse over opposite. You see it's the reciprocal of sine. We have secant, which is hypotenuse over adjacent, that is the reciprocal ratio of cosine, and cotangent, which is adjacent over opposite. Example 1, evaluating trigonometric functions. Evaluate the 6 trigonometric functions of the angle theta. We have a right triangle, we have our reference angle theta, and we're only given the distance of the legs, 5 and 12. We don't know the hypotenuse. So let's figure out the hypotenuse. This is a right triangle. We can use the Pythagorean theorem. A squared plus B squared equals C squared. We're missing the hypotenuse, which is C, so we have 5 squared plus 12 squared equals C squared. That's 25 plus 144 equals C squared. 169 equals C squared. C is 13. So the hypotenuse here is 13. This is a 5, 12, 13 right triangle. It's maybe one you're familiar with. Okay, so now I have all 3 sides of my triangle. Let's label them as the hypotenuse. That is H. It's already labeled. We have the opposite side, so I'm looking opposite theta is 12, and then adjacent or next to is 5. The 6 trigonometric ratios are the sine of theta, the cosine of theta, the tangent of theta, and then we have cosecant of theta, secant of theta, cotangent of theta. And though it's right above, I'm going to write out how I remember these ratios, which is SOHCAHTOA, but I'm a terrible speller. So when I was in geometry class and learning this, one of my classmates actually made up a nonsensical phrase that I use. So I have to say, some old horse came hopping through our alley. And what this does is it tells me that sine is opposite 12 over hypotenuse 13. Cosine is adjacent 5 over hypotenuse 13. Tangent is opposite 12 over adjacent 5. And now I have lined it up as such because The trigonometric ratios on the bottom are just reciprocals of the ones above it. So cosecant is going to be 13 over 12. Right, I'm just flipping the fraction of sign. Secant is 13 over 5, and cotangent is 5 over 12. Example 2, evaluating trigonometric functions. In a right triangle, theta is an acute angle and sine theta is equal to 4 over 7. Evaluate the other 5 trigonometric functions of theta. We're missing a diagram, but we're given enough information that we can create our own. We have a right triangle. We know an acute angle is theta. That simply means the right angle is not theta. And we have the sine of theta, and sine is opposite over hypotenuse. So the side opposite this angle is 4, and the hypotenuse is 7. I'm missing one of the legs. I will use the Pythagorean theorem to find out this missing leg. So I have 4 squared plus b squared equals 7 squared. 16 plus b squared equals 49. B squared equals 33. B equals the square root of 33, which is not a perfect square and does not contain a perfect square factor, so I can't simplify it. So this missing side I'm going to leave as radical 33. And now that I have my triangle, this is just a repeat of the example before. I know it says to evaluate the other 5, but it helps me just to do it the exact same way. So I'm going to write out all 6. The sine of theta, the cosine of theta, the tangent of theta, and then we have the cosecant of theta, the secant of theta, and the cotangent of theta. And then exact same, I'm going to write myself my key. Some old horse came a-hopping through our alley. Okay, so the sign is opposite. Oh, I didn't even label these. 4 is opposite. 7 is hypotenuse. Radical 33 is adjacent. Okay, sine is opposite over hypotenuse. Great, that's what I was given. Cosine is adjacent. Radical 33 over hypotenuse 7. Tangent is opposite, 4 over radical 33. Ooh, we have a radical in the denominator. That's not good form. Let's rationalize this ratio by multiplying both the numerator and denominator by radical 33. We'll get 4 radical 33 over 33. Okay, now the bottom row is just the reciprocal of the top row. It's going to be 7 over 4. 7 over radical 33, which is not great. We don't want to have a radical in the denominator. So I'll simplify by multiplying the top and bottom by radical 33. And I instead will get 7 radical 33 over 33. And then the cotangent is radical 33 over 4. See, I could just flip the original tangent before I rationalized the denominator because that moved the radical sign to the numerator. Okay, so I have evaluated all 5, in fact 6 trigonometric ratios, and I've made sure to rationalize the denominator.